In this video, we're going to review transformations of graphs. So stretching, shrinking, shifting, that sort of thing. So first we're going to start off with vertical and horizontal shifts. Meaning, if I have some function, in this case, let me just take, for my example, f of x, my ordinary friend, x squared. There we go. And now I'm going to change the function by adding or subtracting a number c. And in this case, we're going to take c to be positive. Okay? So what's going to happen with the function if I add or subtract the c? Well, if I just add or subtract the c on the outside, just plop it on the end there, I'm going to shift vertically. So this is going to shift my function up c units. And then if I subtract, then my function is going to move down c units. So for example, if I take f of x plus, let me write it this way. Let me write y equals x squared being my f of x, and I'm just going to add a 2, right? Then I just have the same picture, but it just walks up 2 units. And conversely, if I subtract the 2, you know what's going to happen. It's going to go down 2 units. Okay? Fairly straightforward. Now, if instead of just putting it on the end, I actually put it inside the argument, that's going to give me a horizontal shift where I'm going right or left. So the horizontal shift, it's a little bit different than you think, right? Because you always think of plus being positive. So, but if I do x plus, it actually goes to the left, right? So I go to the left c units, and if I do x minus, it goes to the right c units. So why is that? You want to think about, and if you get confused as to why, you're going to just think about it as what you're really doing is you're sort of moving the point at 0. So if I look at my parabola, I look at the point at 0. Now, if I do y equals x plus 2, now the x plus 2, the plus 2 is in parentheses. So x plus 2 quantity squared. If I have x equal negative 2, then I'm going to get 0. So my point 0, 0 has actually moved over left 2 units so that it's actually at negative 2. So if you get confused with whether you're going right or left, you can always just take a point of your graph that's just like an obvious point that you know, some max, min, whatever, and just see where it goes, especially if it's like the point at 0. Right? So then the same thing happens the other way. If I put in x minus 2 quantity squared now, I'm going to move to the right because what had been the point at 0, now if I put in x equals 2, I'm going to get y equals 0. Okay? So just thinking about how those are sort of bad looking graphs, but yeah, that's okay. Thinking about that. Okay, so that's vertical and horizontal shift. Notice that because I'm adding and subtracting, I haven't changed the shape of the graph. I haven't made it thinner or fatter or anything. I'm just moving it around on the plane. If instead I want to make it thinner or fatter, what I can do is I multiply it. Okay? So stretching and shrinking. Okay, so for stretching and shrinking, what I'm going to do is I'm going to take a positive c, but in fact, it's going to be c greater than 1. Okay? And instead of using y equals x squared, I'm going to use sine of x because it's easier to see when it gets stretched or shrunk. Okay? So let's see. What do we have? C f of x. We can multiply by c on the outside. We can divide by c on the outside. We can multiply by c on the inside. And we can divide by c on the inside. So divide by c, I'm going to run 1 over c. Okay? And really this is only two things. You don't have to think about multiply and divide as different, but you just have to think about whether you're using something that's bigger than 1 or less than 1. But it might be easier just to remember it like this. Okay, so in any case, I take for my parent function here, f of x equals sine x, which is a good one for the purposes here, because we know it's bounded between -1 and 1, and that's kind of ugly. That doesn't even look right. Oh, I'm going to fix it. Hold on. That doesn't look any right. Anyway, I don't care. All right, you have a graphing device. You can graph a nice one. Okay, so what happens if I multiply? So this stretches in the y direction. So stretch in y, and this is going to shrink it in y. And so with sine and cosine, we call this amplitude, but with any other function, you can also multiply by any constant, and you'll change you'll stretch it or shrink it in some way. It's perhaps not as easy to see when you don't have that thing that's sort of nicely bounded, but you can see it very easily here, because if I multiply this by 2, right? If I do y equals 2 sine x, instead of going from -1 to 1, I'm going to go from -2 to 2, right? So I'm doubling the size of my function. It's not doing anything in the x direction, right? Because I'm just multiplying it on the outside. Whereas if I do, maybe I'll just do it on the same one. So if I do y equals 1/2 sine x, I'm going to do it like that in dashed lines. Instead of stretching it up, of course, I'm going to shrink it down to 1/2. So the 1 point becomes 1/2. So I've squashed my function because I'm dividing by 2, or perhaps more correctly, multiplying by 1/2. Okay, so that's a lousy graph. I apologize. All right, let's do the other ones. But that's the point, of course, when you're putting it on the outside. When I put it on the inside, we're doing a stretch and a shrink in x. And of course, it's backwards because it's x, right? So if I do cx here, I'm inside, I'm shrinking horizontally. And if I do 1 over c, I'm stretching horizontally. Okay. So if you remember what happens, let's just do y equals sine of 2x. Okay, and I'm going to graph that one right here. Because sine goes between -1 and 1, this is still going between -1 and 1. It's not going up anymore in the y direction, but it's changing in the x direction. So if I look at my original parent graph up here, this is like 0, this is pi, this is 2 pi, right? Now, it would have been great if it was all to scale, but it's not, so we just have to live with this. What's happening now, when I've got that 2 in there, here at x equals pi, right, I have 0. But here, again, similarly to the situation with the vertical stuff, with the stretching, shifting rather, if I put in x equals pi over 2, I get 0. So what's happening is my graph is shrinking. Horizontally, right? I'm scrunching it together. With respect to sine and cosine and tangent, we can talk about the period and how this changes the period and all that. It's not that important for this particular class. Just so you know, but yeah, it changes in this way. Okay? And for any other kind of function, it's going to be the same thing. You might not be able to see it as easily that it gets squashed horizontally, but if you do put that in there, it will get squashed horizontally. And then my other option, right, is now I'm going to put in 1/2 x, which is going to stretch it out horizontally. So now I run out of board space, right? So I've got to make it smaller. Because, well, maybe I won't. I'll just make it the same and we just won't have the whole thing, right? So pi and 2 pi. So rather than my regular sine of x, which would do this, because it's 1/2, I have to go all the way to 2 pi to get back to the sine of pi, right? So this gets stretched out. So that's your horizontal stretch and shrink. Now there's one other thing which we will use quite often, and that's reflection. Okay? So reflection, if you'll notice, we're always multiplying or adding something positive, or not subtracting something positive. Like C was positive, C was going on. It's because it's easier just to sort of remember stuff when you're separating it. So reflection. Reflection, we're talking about what happens when I have a negative. So negative f of x or f of negative x. Remember we talked a little bit about odd and even and stuff. So that's sort of related. For my example here, because I need an example that works for everything, I'm just going to do y equals square root of x. Right? Useful because this doesn't make sense over here, right? Because I can't take the square root of a negative number. So my natural domain here is going to be over here, the positives. Now, if I put a minus, that means the x's don't change, but all the y's become the negative y's. So if I have the minus out here, this is reflecting around the x-axis. So what I'm going to do, all these positive numbers, now it's still the same positive number, I got a minus in front of it, so it just wraps around down here, right? Okay? And what about if it's inside? Well, all the positive x's go to negative x's. So in that case, what I end up doing is reflecting around, let's be able to spell, that's great, the y-axis. And so this looks a little bit weird now. If I write it down here, because it looks like I'm taking the square root of negative x, well, that only makes sense if x is negative, right? So that then again reminds us that what we're going to do is we're going to take this and reflect it around the y-axis. That graph now looks like this. Okay? And of course, what we're going to do in this particular section is put all these together and do them all in different orders to get a thing. I would suggest that when you guys do that, you make separate graphs, maybe in the corner, and then get the final one in the end. If you want to draw how you're reflecting or stretching or shrinking your graph.